Hey everyone, hope you all can hear me. A very good evening to you all, and hope you all are fine at your homes. So, today we are going to look at a very interesting problem. I hope you all can see my screens as well. So, we are going to look at a very interesting problem which has been very popular across coding interviews. So, it has been asked in the coding interviews of top tech companies like Google, Amazon, and many others. And this has also been a popular question for almost all companies where they have been repeatedly asked. Or this particular question that we are going to discuss today, you can understand it as one of such principal questions which help you understand the concept behind a lot of questions. So it actually stands as a precursor to a whole lot of domain of questions and interview patterns. Okay, so let us look into it. The question basically is titled as sliding window maximum. I hope this writing is visible to you. So this is the question, sliding window maximum. Now, in any kind of question which is asked to you in interviews, there is usually a set of requirements or set of expectations that the interviewer has from you, that how you're applying your knowledge of algorithms or data structures to solve the problem efficiently. So there is a question of efficiency, that is how in how good with what good statistics you can solve that problem, and so on. And using that particular approach, there are two things that principally comes. One is the data structure, another is the algorithm. So now how they become distinguished is a data structure is basically the structure that you will be adopting to solve that problem, and algorithm is basically the set of steps that you will be taking to solve that problem. And in certain cases, the choice of either of these in the best manner helps in solving the entire problem most efficiently. So the interviewer often likes to check through one or two questions whether you can make the choice of data structures very good, and in other set of situations whether you can choose the algorithm pretty good. And in some real life cases, you will see that both are important. They're important together. But in this question, we'll actually analyze it, through the lens of all the domains of computer science, programming structures that we have known, and algorithms, common algorithms that we are aware of. We'll actually view this particular problem, and we'll see how good we can do with it. So this is what the problem says. You have got n numbers. So within an array, suppose you have got n numbers, something like this, like you can have 5, 3, 4, 7, 2, 3, 6, 9, 2, 5. Suppose you have these 10 numbers. So now the question may require that right from the first to the end, the number of windows. I'll come to what it exactly means. So the number of windows or number of subarrays of length k. So some k is given. Suppose k is equal to 4 over here. So the number of subarrays, or basically the subarrays of length 4, are these. You can have the first 4, you can have the second 4, you can have the 4 starting from here, and you can have so on. You can start from here and you can go up to here, you can start from here and you can go up to here, and you can start from here and go up to this particular, I think, yeah, second element. And last choice is to start at 6 and you can go up to 5. So there are so many choices, right? So you can choose all of them. So now what we are interested in is that suppose there is a person over here, there is a person who is distributing something, and every customer requires this amount of time to deal with him completely. Okay, so he's actually at the customer support some kind of place, and he is looking to help them out with their requirements, and for all of them you have these as the time intervals that they require. And now you want to know, or now he wants to know, excuse me, that at every such every such situation where he has 4 persons in front of him, what is going to be the maximum time that they are going to take. So for the first 4, he wants to know what is the maximum time that either one is going to take. Then he wants to know what is the maximum time that the next 4 wants to take. Next 4 means he starts from the second number and the second person and goes up to the fifth person. So what I want to know from you is that suppose it is going up to n, it is starting from 1. So we want to look at subarrays like this, where I is greater than equal to 1 and I plus 3 is less than equal to n. Both should hold. Okay. If both of them holds, then for every I, we basically get a particular subarray. So how many subarrays are there? Over here you can see that I can range from, I basically belongs from 1 to, if it is 1 index, 2, 3, 4, 5, 6, 7. So you can go up to 7, and you can understand through calculations, through your basic elementary mathematics, that the number of subarrays is going to be up to n minus k plus 1, right? So for the subarray which is starting at this particular index n minus k plus 1, after that there is going to be k minus 1 elements. So the last element for this particular subarray is going to be n. So from that you can actually figure out that this I will vary from 1 to n minus k plus 1. These are the total number of subarrays, and in every subarray there are k elements, and the question simply is that return me the maximum element you get in this. So suppose let's talk of a simpler example, something like this: 3, 1, 2, 4, 5, and suppose k is equal to 3. What can we say? In the first 3 elements the highest is going to be 3. In the next 3 elements, the highest is going to be 4. In the next 3 elements, the highest is going to be 5. Simple as that. So here you can see in the first case, we had 3 occurring as the first element. But then it happened that 4 is the last element in the subarray. It can be anything. It can be shown that it can be anything, any element of the subarray. It can be the middle element, it can be the leftmost element. And we need to find out for all these n minus k plus 1 subarrays, we basically need to find out for all these n minus k plus 1 subarrays, what is the maximum element? And this is basically the maximum element. If you observe over here, n is equal to 5 in this example, k is equal to 3. We know that n minus k plus 1, it is holding our calculation. You can say the value is equal to 3, and yes, you have exactly 3 subarrays. One is this one, the second one is basically this one, the third one is basically this one. And the question is as simple as it's observed. You have to find that as the window slides from the first k to the second k to the third k and so on, you need to find the maximum value in every subarray or every window, which is of length k. How to approach this question? So this is exactly how the interviewer is going to introduce you. I just explained it with all this n minus k plus 1. That may be asked to you, or maybe that will be left open. The question how it is introduced is that this is an array. You have to take in windows of size k, and you have to return me for all those windows in order what are the maximum elements. And he will usually give you one such example as we gave in this case. He will give you one example and he will give you the answer for it, so that he is sure that you have understood the question. And as we mentioned, as we discussed before this, as I mentioned before this, that we need to solve it in an efficient manner. So if you just solve it in a brute force manner, if you just think that, okay, we'll not use any optimizations, we'll do as it goes. So we'll first take the first k elements and we'll find out the maximum. Then we have these k elements, the first k elements. When we have to take the next one, we have to also forget this. So this forgetting task might be a bit difficult. So we will take another subarray where we will basically take all the new elements in the new window. For the new window, we'll be taking all the new elements. So one element is being skipped out, another element is being taken. And for all these windows, what I'll say, I'll basically form these small arrays, and for each of them, I'll be calculating the maximum. It's pretty intuitive that from here we can do that kind of, we can adopt that kind of a strategy. We can first take 3, 1, 2, so we'll take 3, 1, 2 somewhere, and we will say the maximum is going to be 3. Then we will take 1, 2, 3 in some array, 1, 2, 4, and we are going to say the maximum is 4. What is the time complexity? Or to talk in mathematical terms, what is the number of operations that you take? What is the number of operations that you take? in order to calculate this entire thing. It goes something like this. How many subarrays have you got? You basically have got n minus k plus 1 subarrays, right? Pure mathematics, nothing unusual. You have got n minus k plus 1 subarrays, and for every subarray you are doing an independent operation. That I have got k numbers with me, I am going to calculate the minimum. Maximum. So for every subarray you can say that I require to do k operations in order to find out which is the best element for me. So after doing k operations, you know that, okay, after seeing all the elements and using a simple maximum kind of operation, you know that 3 is going to be the maximum element. Simple max operation over a subarray. And you can do the same thing over all the subarrays. So it takes k steps for a single subarray. So what is the total number of steps for all the subarrays taken together? So we can say in k steps you can give me the answer for the first subarray. Similarly, in k steps you can give me the answer for the second subarray. Over here, all of them require 3 steps because there are 3 elements in every subarray, but it depends on k. There will be k steps basically. So what can we say over here? We basically, for this last element also, we require to have k computations. So what is the total number of computations? Can we say for every subarray it is k, and the number of subarrays is n minus k plus 1. So the total number is going to be something like this: k into n minus k plus 1. So if you choose k is somewhere around n by 2, suppose n is even and you have chosen k equal to n by 2, what can you infer from here? What will the value of this, suppose f of n comma k, going to be, which is basically the time taken for a certain value of n comma k? F of n comma k is going to be equal to n by 2 multiplied by n by 2 plus 1, n minus n by 2 plus 1, which is greater than or equal to n square by 4. So if n is about 10 to the power 5, this will take around 0.25 into 10 to the power 10 operations, which is quite large, more than 10 to the power 9. So you won't be able to you won't be able to run all of them in 1 second. Make sense? So there you go. Now you know that this is a large number of operations, and for k is equal to n by 2, you also know some, like you can apply mathematics, your derivatives, and you can find out that about around n by 2 you will get the greatest value. How you can find out? Simply like this is, suppose n is a constant. Suppose for a certain n you want to find out what is the best value, so it will be something like this: if k equals to k into n minus k plus 1, and then you can say that this is exactly equal to nk. I'm slightly digressing because I think some of you might be interested in the mathematics, and if you can pour down this mathematics in front of the interviewer, he'll be really, interested in it. He'll really feel glad that you know the mathematics behind this. So you can find out the derivative, and the differentiation will basically take you like this. It will be n minus 2k plus 1. The derivative, we know this is equal to 0. So you'll have n equals to 2k minus 1. So k somewhere turns out to be n plus 1 divided by 2. So if it is an odd number, then you know you are getting an exact element. Otherwise, you know that it will be somewhere between the two middle elements. So you'll get it somewhere in between, which means essentially if you round it towards the top or towards the bottom, you're going to get the best element. So arithmetically, you can find out that this is how it will behave. And if you have some idea about unimodality of functions, you can verify that this function is actually unimodal. It will have something like this. I think it is maximum. So we are talking about the maximum, so it will have something like this. At k equal to 0, you will basically have 0 over here. At k equals to n also, you'll have n over here. I think at k equal to 0 it is 0, and at k equal to n it is 1. It is n. It will be n, so it will be somewhere around here. Maybe it may be n. And over here it is going to be about n square, which is going to be greater. Okay. Over here, if you place k equals to n by 2, you're going to have n square by 4. So you can play with these values. You know that n square is going to be asymptotically greater. Cool. So you know that this naive algorithm is actually taking a lot of time. So how can you actually better this? The idea is that whenever you are shifting from one subarray to another subarray, you are forming the elements once again. You are basically adding the elements once again, and that is actually consuming the time over here. So the first thing that the interviewer will actually look at you with, the kind of idea that he will have when he will continue the interview with you is, you can identify where you're doing inefficiently. Because a person who can identify where he is doing inefficiently, in the long run he can find out the efficient ways of doing it. And it is not necessary that everything will have already a ready-made efficient way of doing it, but if you have the ability of finding the inefficiency in things, you can solve it. So here there are two important things. First of all, when you solve it for an entire subarray, say from here to here, and now you want to search, you want to find out the maximum from here to the next element. The thing is, you have to do extra k operations. However, out of all these elements, you had already compared it. You cannot utilize this knowledge, and the problem is that you need to somehow forget this element. Since you don't know how to suddenly forget this element, that is, after forgetting this element, what will be the maximum? It is not easy to determine that. Through basic programming, you know that it is not easy to determine that without any data structures. So we know that we have to calculate it once again, so that we exclude it manually or programmatically. We are excluding this, hence you have to again compute it over here. In order to make this task easier, what we can say is, we can use a data structure red black tree. Now don't run away if this is a bit advanced to all of you. Red black tree is nothing but the tree set that you have already done. Tree set in Java or set in C++. So this is C++ set, or you have Java tree set. So any self-balancing binary search tree if you use, and if you port these elements, then you have the ability of removing this element in login time. So you can add every element in login time, and you can remove every element in login time, and actually you can remove it in log k time, because k is going to be the number of elements at any point of time. You are going to remove this and then you are going to add something. So if you have this kind of a structure, what is important, that if there are equal elements, you need to preserve them differently. So if there are equal elements, you can preserve them as pairs. You can keep them as pairs where they will have the indexes as well. So in that manner, you can store it. One another way is using multiset. In multiset, you can again store multiple values. So you have many different options. But we can understand that our total, for all the elements, we'll have this kind of a log k kind of computation, maybe twice, maybe thrice, maybe any constant number of times, and the total number of computations will basically go up to n log k, and k can range up to n. So basically this will, you can say that when k goes to n by 2, or maybe greater than that, it depends on the implementation, it will always have some or the other case where it will face n log n. But yes, we have bettered it. The moment we have moved from the scale of n to logarithmic scale, we have bettered it. So all these computations, whatever we did using these complex ideas and using these rather, I think, common structures, you might have used it sometime. You can use a tree set, and this will, believe me, be the intuition, the most common intuition for any comparative programmer who has used hash sets many a time in programming. And you will, before thinking, you will apply this, that okay, if we sort it, then we can use it better. The question is how to remove this. So if you keep a kind of heap, then the problem is that removing the randomly, the first element will be difficult. You have to find that element and then you have to remove it. If you use a red black tree, then the removal will be easier. So in this way, there are a few differences between heap and red black trees. But yeah, you can solve it on, if you use something like tree set and set, which are very common, you can solve it in n log n time. Make sense? Okay, so that brings us to the point of our final solution, that is it the best? Like you show this to any any interviewer, you explain this very well. There is only one question which is awaiting you: can we do better? So about 99% will utter the same thing. Some people will say that can you think of more efficient than this? Otherwise those four words are going to remain exactly the same: can we do better? That's it. So in order to clear the interview, or in order to at least satisfy the interviewer and leave the decision for the next levels, you need to find out the optimal solution, or rather the optimum solution. What you can do in the best possible manner for this. In other words, can we improve this? And for that, the reason why the interviewer won't readily like this approach is because we are taking the help of a structure and there is no observation associated with this. You are absolutely not making any extra observation. What you're doing is you're exploiting the capability of a data structure to handle your data more efficiently. But what the interviewer will be more interested in is what observation you make and what kind of a command you have on the data structures to bring the solution, the optimality of the solution better by exploiting the data structures. So there the observation and knowledge of data structures plays the equally important role. And hence from here, however you might have felt about these things that I've talked about, you can be casual about them. Think about these two approaches, order n square approach and order n log k or n log n approach. Think about them in your own way and then think about how we can do better. And after you have thought well on it, proceed to next part, which is going to be the most important part of this video, where I'm actually going to tell you how the interviewer will expect you to tell him. Okay, so let's pay attention. Let's take an example for this part and let's start on a fresh page. You have a kind of array which is something like this. I hope it is continuing. Let me just check. So yeah, it looks fine over here. Suppose you have something like this: 3, 5, 1, 6, or suppose 1, 4, 2, 6, 3, 5, 4. Okay, so I think 9 elements are there. These are the 9 elements we have selected, and let us see, suppose k equals to 4. Let us see all these subarrays and let us look at it very minutely. We have 3, 5, 1, 4. I'm sorry, we have 3, 5, 1, 4. Next time we have 5, 1, 4, 2. The next part we have 1, 4, 2, 6. The next one we do have 4, 2, 6, 3. The next one we do have 2, 6, 3, 5. And the next one we have 6, 3, 5, 4. Okay, these are your subarrays. Now observe very minutely. In the first case, we are seeing 5 over here. We are seeing 5 over here and 3 is getting eliminated. 5 is going to be the maximum element. We are getting 5 over here and okay, the same thing over here. Look over here. Over here, can we say we are getting 6 and 6 is going to be the maximum element. And all the previous elements are less than 6, right? They are less than or equal to 6. What I can say is the last element is now the most important element to me. Not just the last element, maybe some element which is greater than all these elements, that is, greater than this, and that is important to me. Now, observe the next step. Can I say that here also, along with 6, you have the same 4 and 2, which are again useless. So long as 6 and these 1, 4, 2 are going to coexist, 1, 4 and 2 are going to be useless. And now observe from here up to here. In all the steps, whenever 6 is going to appear, or whenever any of these is going to appear, suppose you have 2 over here, you can see 2 occurs over here, 2 occurs over here. Definitely 6 is also going to appear. Why? Because the window is gradually moving forward. So if some previous element, which is 2 in this case, occurs in the array in some next steps, then 6 is also going to appear, and every time 6 is going to override its importance. हम क्या बोल रहे हैं कि देखिए इधर 6 से पहले 2, 4, 1 ये तीनों चीजें आया है. एज वी आर मूविंग फॉरवर्ड, यहां पे हमने देखा था कि 6 के लिए ये सब यूजलेस हो चुके हैं, अनइम्पॉर्टेंट हो चुके हैं. एज वी आर मूविंग फॉरवर्ड, जब भी ये पिछले एलिमेंट्स है हमें पता है 6 भी रहेंगे, क्योंकि हम आगे मूव कर रहे हैं. तो जो आगे प्रेजेंट है वो तो हमारे पास रहेगा, जो पीछे प्रेजेंट है वो धीरे धीरे गायब हो जाएंगे. बट जो आगे प्रेजेंट है, जैसे ये 6 है, 6 कभी पहले गायब नहीं होगा. 6 will always stay whenever 4, 2 or only 2 is staying. And what can we say? Whenever they stay together, इन दोनों का रहना बिल्कुल ही बेकार है, इसका रहना बिल्कुल ही बेकार है. सो वेन एवर यू सी दैट 6 आपका इधर आ गया और उसके पीछे वाले उसके सामने जो भी एलिमेंट्स है 1, 4 एंड 2 है विच आर टू द लेफ्ट ऑफ 6 जितने भी एलिमेंट्स है, वी कैन से जैसे ही हमने देख लिया कि वो सब छोटे या फिर सेम है, हम क्या कह सकते हैं, दिस 6 हैज द पोटेंशियल टू ओवरराइड देम। अगर सेम भी हो गया हम कह सकते हैं किसी भी 6 को हम प्रायोरिटी दे सकते हैं। और हमें क्या पता है कि राइट एलिमेंट जब भी नेक्स्ट स्टेजेस में जब भी ये 4 2 इनमें से कुछ भी रहेगा 6 हमेशा रहेगा एरे में, क्योंकि ये जब गायब हो जाएगा, सपोज इन नेक्स्ट स्टेप सपोज वी हैव 3 ओवर हियर, देन वी विल हैव वन अदर स्टेज वेयर वी विल हैव 3 5 4 3। तो यहाँ पे हम क्या देख रहे हैं, 6 जब गायब हो गया यहाँ से, तब उसके लेफ्ट में भी सब कुछ गायब हो गया, क्योंकि लेफ्ट से एक एक करके गायब हो रहा है। तो हम क्या समझ सकते हैं इससे, कि जैसे ही हमें राइट में एक बड़ा एलिमेंट मिल गया जिसके लेफ्ट में सब उससे छोटा है, हम क्या कर सकते हैं, ये छोटे वालों को हम बोल सकते हैं ये बेकार है। फॉर द करंट सब एरे तो बेकार है ही, क्योंकि हमें बड़ा एलिमेंट मिल गया है। फॉर ऑल द नेक्स्ट सब एरेज इट इज गोइंग टू बी यूजलेस वंस अगेन, बिकॉज द ग्रेटर एलिमेंट इज गोइंग टू ओवरराइड इन इंपॉर्टेंस। सो दिस इज द की ऑब्जर्वेशन. This is the key observation. So once you say that yes, I ignore these elements because they are unimportant to me, हम ये कह सकते नेक्स्ट टाइम हमारा कंपैरिजन ईजी कर दिया, इट हैज मेड इट ईजियर. ओके, सिमिलरली लुक ओवर हियर, जैसे हमने बोला कि ठीक है यहाँ पे 3 है यहाँ पे 5 आ गया, हम सीधे इसको निकाल सकते हैं. इसके बाद 3 ऐसे ही निकल गया क्योंकि लेफ्ट में था, बट इवन इफ इट हैड नॉट बीन रिमूव्ड, अगर ऐसा भी कुछ होता कि हाँ यहाँ पे 5 3 5 था शुरू में, तो ये 5 आके क्या बोलेगा कि तुम पूरा हट जाओ. ये 5 आके ऐसा बोलेगा. सो अगर ये हटा देंगे तो उसके बाद हम कह सकते हैं कि हाँ इसके बाद अगर कुछ और आ जाएगा जिसमें हमें इस इंटरवल की ज़रूरत पड़ेगा, इस 5 ने इसको हटा के अच्छा ही काम किया, क्योंकि दिस 5 इज ऑलवेज गोइंग टू बी सुपीरियर टू दिस वन एज वेल एज दिस वन. क्यों हमने पहले 5 को हटाया? क्योंकि जैसे ही हमें ये नया 5 मिल गया, ये 5 वही काम कर सकता है जो ये पिछला 5 कर सकता है, वो सारा काम ये नेक्स्ट 5 कर सकता है. दिस 5 इज एट लीस्ट एज कैपेबल एज द प्रीवियस 5, बट इट्स कैपेबिलिटी इज इवन मोर. क्यों? क्योंकि जब इसके बाद कुछ एलिमेंट्स आएंगे, हो सकता है कि ये 5 हट जाएगा एरे से, हमारे लेफ्ट से एलिमेंट्स हट रहे हैं, तो हम कह रहे हैं कि लास्ट वाला मेंटेन करो, क्योंकि वो ज़्यादा ड्यूरेबल है, ज़्यादा दिन तक रहेगा हमारे साथ. सो दिस इज एक्चुअली द की आइडिया विद विच वी स्टार्ट. कुछ और ऑब्जर्वेशंस हम मेक करते हैं ओवर हियर. फ्रॉम 5 कैन वी से दैट दिस 1 इज यूजलेस? थिंक अबाउट इट. और कैन वी से दिस 4 इज यूजलेस? यहाँ पे हम देख रहे हैं कि 4 तो कभी हमारा आउटपुट आ ही नहीं रहा है. इधर पे हमारा 5 आया, देन नेक्स्ट 6 आ गया. बट ऐसा भी कुछ हो सकता है राइट, कि 3 5 1 4 2 3. तो हम क्या बोलेंगे कि 3 5 5 तो आगे 3 को हटा देगा, फिर आएगा 1. अगर हम 1 4 के यहाँ पे हटा देंगे, फिर इस सब एरे से हमें 4 कैसे मिलेगा? इस सब एरे में तो हमें 4 चाहिए. सो जब हम आगे मूव करेंगे, ऐसे सब एरेस फॉर्म करेंगे, इसके आगे वाले तो रिप्रेजेंट करने की कोई मतलब नहीं होता. बट हाँ, जब 4 आ गया मेरे पास, मैं ये कह सकता हूँ कि इस 1 को हम हटा सकते हैं. इस 1 को हम हटा सकते हैं. व्हाट इज द रीजन? बिकॉज दिस 1 इज नो लॉन्गर इंपॉर्टेंट. जब मैं आ गया हूँ, जब भी ये 1 रहेगा मैं तो रहूंगा ही, क्योंकि अब राइट में एडिशन होगा, लेफ्ट में डिलीशन होगा. तो हम कह सकते हैं जैसे ये गाड़ी आगे बढ़ेगा, मैं तो रहूंगा. अगर आई 1 में रहेगा कुछ भी, लाइक उसके रेंज में 1 अगर लाई करेगा तो मैं भी लाई करूंगा. दिस इज एक्चुअली द आइडिया. बट वी कांट से अबाउट 2 एंड 3. वाई? इसके बाद हो सकता है सारे 1 आने लगे, तो हम कह सकते हैं कि हाँ 3 तो फिर इंपॉर्टेंट रहेगा. तो ऐसा नहीं हो सकता कि 4 आके 3 को भगा देगा. वी कांट डू दैट. बट हाँ 3 आके अगर 2 को भगा दिया, वी कैन डू दैट. So this is actually the idea. Form it very well in your mind, and then think about the next statements that I'm making. Don't just take points, in succession. Think about whatever I have mentioned and then understand how we are utilizing it. So हम क्या कह सकते हैं कि at any moment जब हमने विंडो बना लिया और हमने ये इंश्योर किया कि जब भी हम राइट से कोई एलिमेंट घुसा रहे हैं, हम उसके लेफ्ट के जो भी छोटे एलिमेंट्स उसको इमीडिएटली मिल रहे हैं, हम सब हटा दे रहे हैं. हम कुछ ऐसा कर रहे हैं कि पहले हमने 3 को घुसाया था, फिर हमने 5 को घुसाया, 5 घुसा के हमने कहा कि 3 को हटाओ, फिर 1 घुसाया, फिर हमने कुछ नहीं किया, फिर हमने 4 घुसाया, तो हमने कहा कि इस 1 को पहले हटाओ क्योंकि ये इंपॉर्टेंट नहीं है. इस समय जब ये 4 एलिमेंट्स आ गए, हम क्या कह सकते हैं कि हर बंदे ने अपने लेफ्ट में बस अपने से बड़ा एलिमेंट ही रहने दिया है. अपने से छोटा ये इक्वल एलिमेंट सबको भगा दिया है हर एक एलिमेंट ने। तो हम क्या कह सकते हैं यहाँ से कि अभी जो प्रेजेंट सिचुएशन है, कुछ एलिमेंट्स छोटे थे इसलिए भगा दिया हमने। हमने प्रूव किया कि दे विल नेवर बी रिक्वायर्ड। बट इन एनी स्टेट कैन वी से कि करंट जो चीज़ें हैं हमारे पास, उसमें लेफ्ट पोजीशन में, इन द लेफ्ट मोस्ट पोजीशन वी हैव द ग्रेटेस्ट एलिमेंट नाउ। कैन वी से दिस? तो हम कैसे बोल पा रहे हैं? क्योंकि हमने छोटे एलिमेंट पहले, लाइक हर एक एलिमेंट जो अभी हमने इस स्ट्रक्चर के अंदर रखा है, हर एक एलिमेंट बोल रहा है कि मुझसे बड़े एलिमेंट ही हो सकते हैं मेरे लेफ्ट में। तो अगर हम लेफ्ट मोस्ट एलिमेंट को चुने, क्या कहेंगे, लाइक इस स्ट्रक्चर में क्या होगा अगर ऐसे कुछ एलिमेंट्स हैं a1 a2 a3, क्या कहेंगे? a3 is less than this, a2 is less than this, so this is always going to be the greatest, right? तो हम इसी को ले सकते हैं, हम डायरेक्टली बोल सकते हैं कि हाँ सही है। फिर नेक्स्ट टाइम जब हम आगे मूव कर जाएंगे, हम क्या कर सकते हैं? हम सिंपली कहेंगे कि 2 को तो घुसाना है, एंड 2 को घुसा दो चुपचाप। 2 किसी को रिमूव नहीं कर पाएगा, 2 इज लेस देन 4, सो लेट्स कीप इट। लेट अस सी, इज 5 स्टिल इन द रेंज? इस स्ट्रक्चर के शुरू में अगर 5 स्टिल अगर रेंज में नहीं है तो हम कुछ और करते, बट अगर रेंज में है तो सिंपल यही अभी लार्जेस्ट है, तो इसी को फिर से 5 को रिटर्न करते, तो वी हैव 5 एंड देन वी हैव 5। देन लेट अस ऑब्जर्व इट। जब हमें 1 मिला, जब हम आगे बढ़ के और इधर हम लोग कहीं पर रेस्ट कर रहे हैं, व्हाट कैन वी सी? नाउ वी हैव रिमूव दिस, बट सी वी हैव ऑलरेडी रिमूव्ड 1। ये जो 1 ही हमने रिमूव कर दिया, बट सी हमारा हाइपोथेसिस क्या था? इसको 4 ने रिमूव किया। 4 ने क्यों रिमूव किया? क्योंकि 4 इससे बड़ा है। एंड वॉज 4 रॉन्ग? नहीं, 4 हमारे पास है, तो डेफिनेटली हमने 1 को रिमूव करके कुछ गड़बड़ नहीं किया है। 4 इज देयर टू हेल्प अस करेंटली, 4 अभी तक भागा नहीं है, सो इफ 1 इज रिक्वायर्ड देन 4 इज गोइंग टू बी देयर। हम कह सकते हैं 5, हमारे 5 को ही हम स्किप कर रहे हैं, तो 5 को हटा देते हैं यहाँ से। दिस इज समथिंग दैट वी डू। देन व्हाट कैन वी से कि हाँ अभी 4 है और अभी ये नया एलिमेंट 6 मिला है, तो 6 को एंटर करते हैं। जब 6 को एंटर करेंगे तब हम क्या कहेंगे? 6 तो एंटर करेगा, बट इससे पहले इन सबको हटा देगा जो भी 2 और 4 प्रेजेंट है। तो अभी 6 अकेले बैठा हुआ है कि मुझसे पहले कोई भी एलिमेंट अब इंपॉर्टेंट नहीं है। मैं इधर आ गया, इसको बोल दे कि इधर इस सब एरे के लिए 6 है। अब तुम नेक्स्ट सब एरे देखो, नेक्स्ट सब एरे देखो, कुछ भी सब एरे देखो जिसमें 4 2 या ये सब बिलोंग करते हैं, 6 इज गोइंग टू ओवरराइड देम इन टर्म्स ऑफ द इंपॉर्टेंस। सो बाय नाउ यू मस्ट हैव गॉट द आइडिया कि हम कैसे एक विंडो को या फिर एक स्ट्रक्चर को मेंटेन करते हुए आगे बढ़ रहे हैं। हम बोल रहे हैं कि उसको हम एंड से घुसाएंगे, राइट से हम घुसाएंगे, और घुसाते समय हम राइट से कुछ कुछ चीज़ें निकालेंगे। विल बेसिकली रिमूव सर्टेन वैल्यूज जो हमारे लिए अनइम्पॉर्टेंट है। अब आप कह सकते हैं कि हमने यहाँ तक रिमूव किया कुछ वैल्यूज, और फिर यहाँ पे कुछ वैल्यूज हमने रिमूव नहीं किया, इधर पे मान लेते कुछ 5, यहाँ पे कुछ और रिमूव नहीं किया। क्या ये नहीं हो सकता कि ये अब बेकार हो गया बट ये ज़रूरी है? नहीं, ऐसा तो नहीं हो सकता, क्योंकि हमें पता है कि ये इधर इंक्रीज कर रहा है। तो मान लेते इधर हम 4 घुसा रहे थे, इसलिए 4 से कम एलिमेंट सारे निकल गए, 4 या 4 से कम। और इधर हमने 5 फेस किया तो हम कुछ निकाल नहीं पाए 5 का। हमें क्या पता है कि बाय दिस प्रॉपर्टी इधर सब कुछ 5 से ग्रेटर होना चाहिए, तो 4 कैन नॉट रिमूव एनी अदर एलिमेंट। वी नो दिस। सो ये हमें बेसिक चीज़ें मिल गया। व्हाट एल्स कैन वी से बाय लुकिंग एट दिस? कि हमारे स्ट्रक्चर में क्या क्या काम ज़रूरी हो रहा है कि जब हम ये विंडो स्लाइड कर रहे हैं, द फर्स्ट एलिमेंट नीड्स टू बी चेक्ड दैट इज इट इक्वल टू द फर्स्ट एलिमेंट इन दैट स्ट्रक्चर। क्या जो एलिमेंट मैं स्किप कर रहा हूँ वो ही मेरा फर्स्ट एलिमेंट है उस स्ट्रक्चर में? अगर वहाँ पे वो ही एलिमेंट मेरा लाइक उस स्ट्रक्चर में पहला एलिमेंट है, तो उसको हटाना पड़ेगा। एट अ टाइम मैं एक ही स्टेप शिफ्ट कर रहा हूँ, तो मैक्सिमम एक ही एलिमेंट मेरा कॉमन हो सकता है इफ इट हैजंट बीन रिमूव्ड। सो व्हाट विल आई से? साइलेंटली रिमूव इट, और तुम्हें ग्रेटेस्ट एलिमेंट मिल जाएगा। फिर जब तुम ऐड करोगे पीछे से तब तुम्हें मिल जाएगा। सो व्हाट कैन वी से नाउ? कैन वी हैव द गारंटी कि हमेशा हर एक विंडो के लिए जब हम सामने से कुछ हटाएंगे और पीछे से कुछ हटाकर फिर बिठाएंगे, हमेशा ये बिठाने के बाद ज़रूर एक ना एक एलिमेंट हमारे पास रहेगा? वाई? बिकॉज जब हम एक लास्ट एलिमेंट घुसा रहे हैं, सपोज 6, हो सकता है उसने सब कुछ निकाल दिया, बट वो खुद तो रहेगा ना, वो खुद तो रहेगा। एंड क्या हम जब लेफ्ट से रिमूव कर रहे तब क्या 6 को हटा सकते? नहीं, लेफ्ट से जब रिमूव कर रहे वो उसी को हटाएगा जो उस विंडो के लेफ्ट में लाई करता है, अगर एग्जिस्ट करता है तो, अदरवाइज वी वोंट रिमूव इट। So this is the idea that we apply in this kind of programs, that as we move forward, we are yeah वी आर गोइंग टू एक्ट स्मार्टली। तो यहाँ पे आप थोड़ा ऑब्जर्व कीजिए कि जब भी कुछ आ रहा है, जब भी एक नया एलिमेंट आ रहा है, हो सकता है कि वो सबको रिमूव करे। तो सबको रिमूव करने में हो सकता है काफ़ी टाइम लग जाए, के टाइम लग जाए। तो फिर से आपका वही आ रहा है कि हर एक विंडो के लिए के टाइम अगर लग जाए तो फिर से विंडो इंटू के इज गोइंग टू बी एन स्क्वायर। बट सोचिए कि कोई ना कोई एक एलिमेंट को आप कितनी बार घुसा रहे हैं एरे के अंदर। यू आर ओनली एंटरिंग फ्रॉम द एंड। आप कोई भी एलिमेंट को आप सिर्फ एंड से ही घुसा रहे हैं। सो एवरी एलिमेंट यू आर एंटरिंग ओनली वंस। एंड एक एलिमेंट को आप कैसे भगा रहे हैं? एक तो आप लास्ट से भगा सकते हैं, जब आप इसको घुसाएंगे तो इसको यदि इधर से निकाल सकते हैं, नहीं तो इसको सामने से निकाल सकते हैं। if its time has passed, if its duration has passed, we can remove it from the front. So जहाँ से भी आप remove करेंगे, let me just check if okay, I hope it will carry it through. So what can we say? हाँ, ऐसे जब deletions होंगे तो क्या ये एलिमेंट्स ये लास्ट एलिमेंट हो सकता है? नहीं। क्या ये एलिमेंट से लास्ट एलिमेंट हो सकता है? हमने शो किया 6 को यूज करके कि 6 कभी ऐसा एलिमेंट नहीं हो सकता जो 6 को इंट्रोड्यूस करते समय खुद ही रिमूव होगा। नहीं, उससे पहले के कुछ एलिमेंट्स रिमूव हो सकते हैं, लास्ट से हो या फर्स्ट से हो। सो व्हाट कैन बी से कि ये एलिमेंट एक बार रिमूव हो जाएंगे तो क्या इन्हें फिर से हम कभी भी वापस ला रहे हैं? क्या ये कभी भी इंपॉर्टेंट हो रहा है? वन रिमूवल इज दैट दिस न्यू एलिमेंट इज कमिंग एंड टेलिंग दैट यू आर वर्थलेस। Another is that it is telling that your time has passed. You have done a good job. Now your time has passed. So please depart. These are the two ways we are removing. So अगर ये remove हम करेंगे तो हम क्या कहेंगे कि अगर ये remove हम करेंगे that means they are not at all important और हम कभी बाद में push नहीं करेंगे. So एक ही बार हम remove करेंगे एक एलिमेंट को. एक एक एलिमेंट को हम एक ही बार रिमूव करें, उसके बाद हम कभी पुश नहीं कर रहे. सो कितने सारे एलिमेंट्स है टोटल n एलिमेंट्स है. पूरा लेफ्ट से राइट जाइए, आपका n एलिमेंट्स ही मिलेगा. हर एक को आप इस स्ट्रक्चर के अंदर एक ही बार डाल रहे हैं एंड एक ही बार मैक्सिमम रिमूव कर रहे हैं. सो वी कैन से दिस इज ऑलवेज गोइंग टू बी लेस देन इक्वल टू 2n. मेक सेंस? तो आप सोचिए n log n एंड 2n आपके कंप्यूटर प्रोग्रामिंग की एक्सपीरियंस देयर मे बी वेरी लेस डिफरेंस, बट asymptotically there is a huge difference. Theoretically n and n log n are not the same thing. They have got a significant difference and hence we have to be particular about each of those things. So even if this constant is a huge constant times n, we say that this is order n and this is better than order n log n. Okay. Sorry, getting the idea without without me discussing the implementation yet, are you able to get the idea how this is going to be an order n kind of an implementation? The idea comes from over here. And it's as simple as that. So that's it. Now what structure can you use? For that you need to know the operations. So we need to insert at the back of the structure. Insert at the back. And remember, if you have to remove a particular element of an array or vector, then that is a time consuming operation. So you cannot use a simple vector for it. So you have to use a special data structure which can do this. You have to insert at the back and you need to remove at the back. You can also call this the rear. You have to remove at the back and you have to remove at the front. They are distinct operations. You can't substitute one by the other. You have to remove at the front. You have to choose a data structure which will support all of these things in very small amount of time, maybe in one step. So you have to maybe cover this in order one time. फिर से आपको पता है कि हाँ ये तीनों चीज कर देता है. कौन सा चीज? आपका रेड ब्लैक ट्री या आपका ट्री सेट. बट ऑर्डर वन में अगर करने की बात आ जाए then that is not always possible. So for this kind of cases we use a DQ. Okay, DQ हम यूज करते हैं which can help us insert from both the ends and remove at both the ends. We use a DQ. So हम DQ यूज करके ये स्ट्रक्चर मेंटेन करेंगे और हर एक स्टेप में हम कहेंगे कि जब हमारा स्ट्रक्चर बन गया करंट इटरेशन के बाद, तो जो सबसे सामने लाई कर रहे वही राजा है. उसने अपने सामने सब सारे ग्रेटेस्ट एलिमेंट को भगा दिया है, बट उसको कोई भगा नहीं पाया. उसने अपने सामने all the elements which are greater than it has removed it. I'm sorry, all the elements which are less than it has removed it. But उसको कोई भगा नहीं पाया. So it is not less than any other element. It is greater than the previous element, that is greater than the previous element, and so on. So we can say just by reading the first element we will be able to do our job. Make sense? So using DQ, how we can implement it, let us quickly look at it. So let's make a code, maybe, yeah, G plus, I'm sorry. Let us write a program, sliding window max.cpp. Let us copy some of my previously written code, say linked lists, okay, and dot slash competitive. Let me check. Okay, I've created within this. Okay, so linked list dot cpp. I'll be copying this into so that I get the template. Okay, and now I'll be opening this. So you have, which one is this? Interview problems, sliding window max. I'll be removing all these things. There you go. So now what can we say? Or let me keep this part, and rest let me remove all these things. So we have something like this. We have n equals to, we can have this in LL as well, vector int v, and that has n values, and we will say that for all the values LL equals to 0, I less than n I plus plus. So we can maybe maintain it uniformly. We'll have LL, which is long int, and I'll be saying that take all these values. So we have not taken the value of n. Take all these values of vi, and then what we can say is now we'll be calculating. Cool. So first of all, we'll be using a dq ll, and this will store basically all our values. Let us return, or we can say window, something like this, and we will not initialize it. We can try something like this. For the first window, we'll be introducing everything, or we can just continue up to the end. We can say that we'll be continuing. So while, what we need to see that whenever we are inserting something, everything that is less than or equal to that coming before it, we should remove them. Now there are two ways of doing it. One, we can store the values themselves, but if you store the values, then checking whether that value is lying in front of us or not, that is going to be difficult. That is, when we are shifting the window to the right, whether that value is retained or that value should be removed, then that will become a question. How should we compare? So it is good to store the positions. What I mentioned is something like this, that when you will be removing this, how will you be comparing? You have to compare with the value if you store the values. So comparing with the values means it does not give you the idea whether it is located in the position that you are removing or some other position. Maybe you can do without storing position as well. Why so? Because you know that if this value is prevailing, it cannot prevail. If it prevails later on, it must be prevailing here as well. So you can directly remove it. So yeah, I'm not denying it that you cannot do it using values, but using positions, you can also say that, okay, for this window, the maximum value lies in this position. You can get a lot of information like that. So you can say that, okay, we are going to store only the positions. So if you have stored the positions, first of all, you need to ensure that when you are checking with the previous elements, there should be some elements previously, located. So you first need to say that the window should not be empty. This should not be empty. And you can say that if it is not empty, then you can check that if window dot back is going to be less than equal to, the v of window back, if it becomes less than equal to v of I, then we can pop it. We can pop it from the back. So we can, pop back, I think should work. Pop back, and there you go. Then you can say that, okay, now I have eliminated all the rubbish elements. So now I can just push back the current element, which is I. Okay. Next, what can we say? That if the first element of this structure is not in the range, we need to remove it. So if window dot front is equal to I minus k suffices, because when I have taken the ith element, that means I'm actually focusing on I minus k plus 1 to ith position. So I minus kth element is nonsense, it's immaterial to me. So I'll be checking whether the position matches. If the position matches, now this is the reason why explicitly I wanted. But anyway, we know that there can be alternatives. So okay, we are going to check it, and if it turns out that yes, it is so, then we'll say that just get lost. So we'll just do pop front. Okay, I hope these functions actually work. We'll test it. Now we say that okay, what can we do now? Yeah, now we can say that once we have done all these things, now the first element is going to be the greatest element that occurs in our current window. So we can just print that if I is greater than equal to k. Now why did I do this? Think about it. Or sorry, greater than equal to k minus 1. Why did I do this? Think about it. If I do this, now I'll be printing window dot front without popping it. I'll be removing it, and I can say that okay, leave some space, and there you go. This should suffice. What can we say now? G++ sliding window max.cpp. Kind of member reference is a function. Perhaps you meant to call it with okay, 1 warning and 9 errors. So there is no k, that is my mistake. I forgot to take in k. C in k. So you have some LLK over here, and you are going to take this. Okay, 7 errors. Now let us see. You meant to call it pushback, popback, window. Okay, let us refer to the implementation. Window DQ in C++. DQ in C++ is a very standard thing. So we can simply refer to these. You have push front, you have push back, you have got front, and you have got back. So there should not be any problem. Maybe the problem was that I used this bracket over here. Now it should work perfectly because there is nothing else. Yeah, there you go. So we can now run, I'm sorry, dot slash, yeah. Now we can maybe use this particular example. We have 3514263554. 92514263554, and we can say that we are looking for 4 elements at a time. So okay, it prints the minimum for all, I think. Is it doing so? 5 1. Okay, fine. So what it is doing, it is printing the index, so you can print the actual values for them in this manner. So when you do something like this, you will get the values. So now you can just copy and paste this. You will basically find it will work perfectly. So you have the 5, which is the first one. Then the next one is also giving us 5 as the maximum. And then 6 starts its regime, and it is going to be 6, 6, 6, 6 for all the ones. If you do a small change, if you say that okay 9, and then I'll be keeping 10 at the end. I'll not be having 4, I'll be keeping 10 at the end. I'm sorry, where did I use that? Okay, I'll be keeping 10 at the end. Then you will use 4, and then you can see last one will be 10. Okay, and we can have a lot more. Maybe one of the examples that we used, we had 3514231111. 3514231111 is 10. So 3514231111. So we want again in intervals of 4. You can see once again. Then the first 4 numbers gives us 5. Then again we have 5, and now 4 is not going wasted. 5 is not removing 4, but you can say 4 is not going wasted. But 4 removed 1, and yes, it did the right thing. We know that. By removing one, it did the right thing. Yeah. So now what we can say is that yeah, the next one is going to be 4 and the next one is like over here is going to be 4 and so on. Okay. Very popular question. We can actually frame, I'm sorry, a lot of questions on this. If you look at one problem in the recent, I think, lunchtime or cook-off. In CodeChef lunchtime or cook-off, I didn't see the editorial, but I think like many people told me that actually the editorial speaks of binary search. But when I solved the problem, I used this technique. So because this technique actually, I don't know what the complexities will compare and what they will give us, but sometimes we can prevent those binary kind of techniques. We can just solve it. You can see we have not done anything unusual. We have just proceeded as simple as that. We have just proceeded progressively. We have not made any twists or turns. So you can see from here that we are going to get this is going to give us an optimal manner. So whenever you do pop back, you can count the steps. You can say that I am going to count the steps, maybe LL steps equals to 0. And then you will say whenever you will pop, you will do steps plus plus. And over here also you are going to do steps plus steps plus plus. Why? Because you are adding one element, and over here the number of elements you are removing, you will again do steps plus plus. So at the end, if you print cout steps, there you go, ndl, and if you try to print it, you will see it must be less than equal to 2n, what we theoretically proved. You can see 2n is 20, so it will be 19. Okay, always going to be like this. You can check for any example. Over here also, like if you check for our previous example, it will be less than equal to 18. It must be. That is the way we are doing it. Okay, it is 15, much lesser. Why is this fluctuating again? If this is asked, why is this fluctuating? Because at the end you're not popping everything. So you're only popping the first element if you think this is irrelevant. But this element, this one, you're popping only when you're introducing a greater element. Otherwise, you're not popping. So if you introduce a greater element, it will remove everything, it will sweep everything, but not always. Okay. So that's it. There are a lot of questions that are based on this or that can be based on this, and this forms a precursor to a lot of programming techniques and programming questionnaire, which lie important for your interviews. And this is important specifically for your placement interviews. So for your internships, some of the companies look for this. If you look at the top companies, they will sometimes look for this, but usually in your placements, many companies will have this expectation that using this DQ we can solve this basic problem. This is called the sliding window maximum problem. It has been asked even recently. I think one of my friends, he has been asked this question in Amazon. So he gave the nlogn approach, and by the way, he cleared the rounds. And later on, anyway, later on it turned out to be hard luck for him. But the fact that I want to convey is that this is important. This sliding window maximum is very important for your interviews. So let us know in the comments, in the comment section, or in the wherever you feel like. You can connect to us and let us know what kind of topics you'll be looking for. If you have any special feedback for me, you can let me know in the same kind of thread. I may sometimes look at that. But yeah, that's it, and take care. If you face any confusion with any of the parts, please go back and watch that part, because I tried to cover as many insights as possible in this video. So I hope that you will understand it very minutely, not just the steps. You would remember all the insights and intuitions that we used in finding out the solution. So that's it. Yeah. And I hope you can solve similar problems in all your interviews. So all the best for your interviews. Take care, stay safe, take care of all your family members, and let me know about this session If you felt it was fine and what you would like to see me covering in the future sessions, do let me know, and that's fine. Or whoever shall be covering, you can let us know whatever topics you want. This session or this particular series that we have started over here is specifically in view of the interviews. So we hope the best of your interviews, and we hope that you can make the best use of it. So thank you. Bye and good night.